on. Are we good? All right. So greetings and welcome everybody to this first exciting edition of 15, 18, 213 and 15, 513. Why are you laughing at me?
Why
not? So what to say? Here we are. And the other end of the camera, there you are. Hope we're all happy to be here. I'm happy to be here. This is one of my favorite classes to teach. I mean, this class has a lot of all sorts of different things that are really useful, right? It's like a candy box of useful stuff because it samples, right, important things from all of our systems classes, right, to get you sort of ready and exposed to the material while teaching some really critically important, some really critically important system skills. Okay, so it really is an important class, and I love teaching it because it's so applied and so much fun. Okay, what to say? The course theme. You know, if you're an undergraduate student or ever were an undergraduate student in computer science, you may remember that at the beginning of your education, we talked a lot about abstraction. Okay. We worked a lot with abstractions. This idea that if you have really complex systems, what you want to do is encapsulate certain functionality, make it into black boxes and ignore it. That if you're trying to understand something really complex, you can't possibly grok all the details at once. So you assemble meaningful building blocks. Whether they're actual, real, tangible building blocks, like building a building out of concrete blocks as opposed to concrete, or, right, code-wise building blocks like modules and libraries, or intellectual building blocks like Big O and amortized analysis, right? And so we focus a lot on abstracting things to get powerful things, represented in a way in which we can use it. And this is a great tool that's important to every aspect of computer science, applied and theoretical. Okay? And it's one that's used from freshman year all the way through graduate education and careers in the computer sciences. But sometimes, in narrow areas, you actually need to blow through those abstractions. You actually need to get down to the details. Whether that's measuring actual performance in actual time rather than throwing away that pesky constant. Right? Or thinking about how something runs or is running on a real computer. And that's what 213 is about. 213 is about doing it for real. Okay? Why? Well, A, to become effective programmers. Right? And B, to be effective students. Right? We do it because it's a critically important skill to the practical programmer. We also do it because it's a critically important skill to learning more advanced computer science, most especially in systems, but also in a ton of other areas. Right? Graphics, databases, all sorts of things. Okay. We've got a bunch of slides here about these great realities. I don't spend a whole bunch of time on these great realities right now because we spend the whole semester diving into the details. But perhaps they're a good example of abstraction in real-world detail. When you were in math classes, you learned about integers. Right? The set of all integers. And integers were really cool, right? Because there were countably infinite of them. No matter what integer you give me, I can give you something bigger. And no matter what integer you give me, I can give you something smaller. Right? Amazing. And there's space between them, yet you can't get there. But computers don't quite work that way, right? Computers have a finite amount of memory. They don't have an infinite amount of memory. They have a finite amount of memory. Yay much. How much is yay much? I don't know. How much memory do you have in that computer? But once we start dealing with real world and real world limits, finite memory, that means we need to have a finite representation of a number. Right? If I only have yay much memory in one case, I can use it all for a single number. That's probably not really useful, right? I probably want to partition it so I can have more than one thing in memory. And say, well, if my memory is yay big, my integers at most can be yay big. And now we start to have real limits. Maybe an integer can only go from, let's say, negative 32,000 or so to positive 32,000 or so now. So now we're talking about a difference between ints, right? The integer representation we have available when programming. Are you recording, class? Yes? No. We provide the only recording. Turn that off. So I'll go ahead and interject right now. There is a policy against electronically mediated communication and recording. Okay? So you're not allowed to IM, text, email, web surf, join chat rooms, IRC, collaboratively edit documents, blah, 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 blah. No electronically mediated communication. So you can use your laptop to take notes. You can use your laptop to look at slides if you downloaded them in advance. Okay? But no electronically mediated communication. Secondly, the only recording of this class is the one that we take. You will have access to it to this semester and this semester only. And then it goes away. Okay? And the reason for that is very obvious. You guys are enrolled students. You're taking 15.213 or 15.513. And quite honestly, you're paying us for it. We're not delivering these videos for free. Okay? 15.213 has a canonical set of lectures. It has a canonical set of labs. It has a canonical set of auto graders. These days, it has an ever-growing set of exam questions and, exam graders. No one out there is going to take our set of materials and distribute them and call it a Carnegie Mellon equivalent program. It's not, right? Because it doesn't have you as a collection of students. It doesn't have our core staff as a collection of people supporting it, right? And we're just not going in that direction. So for this semester, you'll have access to all the video. Once you're done, the video goes away. If you want to refer to things after that, you've got your notes, and you've got the book, and you've got the slides. But there's no recording. Okay? We good? All right. And no electronically mediated communication either. So if you want to have fun, it's got to be, my type of fun. All right, back to this. So once we have finite memory, right, what to say? Now we can't have an infinite number of integers, right? We have relatively few number of integers. So what happens if we have the biggest int that we can represent, and we add 1 to it? It's not going to get bigger, right? Different answers to that question are possible. Maybe it goes into an error state. Flags it as a number that's too high. That happens with floating point numbers, actually. With integers, as you pointed out, it wraps around and becomes the most negative number. And we'll talk about why. Okay? But this is a classic example of why sometimes you've got to be able to look through abstraction into the detail. Because ints, right, look a lot like integers, work a lot like integers. For a lot of problems, they're a great substitute for integers. And then suddenly things don't work the way you think they should. And when they don't work the way you think they should, now you've got to actually understand why, how they're implemented, right? Why it's implemented that way, and how you can make things work that way. Okay? Another issue, right? And it's less of an issue most of the time, and then sometimes it matters. Right? There's no such thing as randomness when it comes to a computer. Okay? At best, we have some approximation of randomness. Right? What happens, right? There's something called a pseudo-random number generator. It's a function where the values bounce around in a way that you really wouldn't predict unless you were using the same function. And then we pick some starting point along this. It's called the seed. And now we get a sequence of seemingly random numbers. So unless you know the generator and you know the seed, it looks like a random set of numbers. Okay? And then how do we pick that seed? Well, what we try to do is get things from outside the computer that approximate random things. Because outside the computer there are random numbers, or randomness at least. And so we try to use things like the measure of time between ports coming to packets showing up at the network, or the value and time between keystrokes, and. Take a whole bunch of system events coming from different sources. that don't have the same force function and hopefully have no discernible force function, and use those to generate a sequence of numbers that we can then use to seed our random number generator. Why not just use these random things? Because there aren't enough of them. If we need a whole bunch of random numbers, we can't collect enough randomness. There's no infinite improbability generator here. Okay? So we use external events that are hopefully a random or approximately random to seed pseudo-random number generators. Sometimes it matters, sometimes it doesn't. A lot of times a pseudo-random number generator is just as good as real random numbers. Sometimes it's better. If something random is provided as input to your program, and then your program dies, you may have no way of figuring out what that was. It was some random event, right? But if we're actually using a pseudo-random number generator, we can provide the same seed and get the same set of events. Much better for debugging, right, to have pseudo-randomness than real randomness. Of course, if that predictability isn't good, then different story, right? Okay. So back in the day, well before my day, people used to actually write significant volumes of assembly by hand. Right? When you look at an assembly file, the extension on an assembly file is .s. Right? .c for C, .j for Java. Right? Why is assembly .s and not .a? Well, the answer is because back in the day, it was the source code. S, source. People wrote assembly by hand and then fed it to an assembler. Okay, to get the machine code. And for a long time, even after compilers became a thing, right, a lot of code was still written in assembly, because quite simply compilers weren't good enough. They could generate code, assembly code from high-level code, but couldn't do it really, really efficiently. They couldn't do it really, really efficiently for two reasons. A, the science of writing compilers just hadn't advanced as much. And B, computers weren't fast enough. Okay? Compilers now build a lot of data structures and analyze a lot of different possibilities to determine the optimal ones. When computers were really slow, it wasn't worth it. No one wanted to wait a week for a compile. Okay? But these days, computers are much faster. The science of writing compilers is much better. We can write really, really efficient compilers. And beyond that, processors have gotten so complicated that humans trying to understand how to code for them efficiently suffer from state explosion. We just can't keep all of the possibilities, all of those states in our head. So humans can't possibly write code as efficiently in assembly as compilers can. There are certain small bits of assembly that humans still write by hand. Okay? Very small bits, usually in the depth of an operating system or embedded system. But other than that, all code starts out as a high level of code. Now, that doesn't mean the programmers don't need to be able to read assembly. In fact, we do. Because the assembly is what's actually executing. Sometimes it's good enough to look at the high level code and assume the assembly does the same thing. But sometimes the details actually matter. And then we need to be able to blow through that abstraction and read the assembly to understand what the machine is actually going to do when it's executing our program. Okay? So, in a traditional engineering class, when one learned assembly, one actually learned assembly by writing it. Writing a bunch of assembly language programs. We don't do that here, because it's not useful. No one writes a bunch of assembly language programs. Even those people who code in assembly don't write programs that could be written in high-level code in assembly. That's not useful. What we're going to learn here to do is read assembly and understand assembly and understand what the assembly is asking the machine to do and understand how that assembly relates to our C code. That way, we can program in C and understand what we're asking the machine to do for real, when we need to, when we care. And we can double check our abstract understanding with a detailed understanding whenever we choose to, by diving deep. For applications like, tuning performance, writing the really detailed bits and hardware-dependent bits of operating systems and embedded systems. Things like fighting malware and viruses. And in very, very, very rare cases, dealing with program bugs. But those are pretty rare cases. Most of the time, the bugs we write in our high-level code are our bugs and are very visible in the high-level code. Memory matters, right? In lower-level courses, when you talk about performance and you talk about algorithms, you don't worry a lot about how big things are, right? In fact, the model for amortized analysis, right, is for n greater than n naught, right? For some problem really large. That analysis is very useful, compellingly important in many cases. But in many cases, the question we're trying to answer isn't, how can I solve this problem with infinite resources for the largest possible case? It's, how can I solve the problem I need to solve, which is maybe yay big, with a set of resources that may be exactly big enough. Okay. So we actually need to manage memory. Think about it. And, one doesn't want to have a rich banker, right? If your banker is rich, what does that mean? You're not. Right? Whose money is the banker spending? Yours, right? Well, we don't want a rich memory manager. We don't want a memory manager that's using all of our memory, do we? Right? We don't want a slow memory manager. We don't want it using all of our time. So we're going to look at how we can manage memory that's in a way that's efficient both in terms of space and time. You guys have programmed in C enough to run into pointer problems, out of bounds problems, freeing things that shouldn't be freed problems. At the end of the day, right, the bugs that exist turn out to be very painful. And people are pretty ill-equipped to find them because we're thinking about the problem we're trying to solve. We're thinking about the process we need to go through to solve that problem. We're thinking about the resources we need to use to solve that problem. We're not necessarily thinking at every juncture about the details of addresses, pointers, sizes, what starts at 0 and what starts at 1. And so those bugs can be painful. Memory performance isn't uniform. In many of our classes, we just say, look, it's in memory and memory is fast. Or it's in disk and disk is slow. But as it turns out, there's a whole memory hierarchy. There are registers that operate at the speed of the processor. Level 1 cache is extremely fast. Level 2 cache that's still pretty fast. Memory that's slow, and disk that's slow as molasses in the winter. Never mind remote storage that's probably twice as slow as that. It's got to go over a network first. Depends on the network, of course. Okay. So we start to think about how it is that we can organize things in memory to try to help things float to the top faster levels. So more of what we use is up here, and less of what we use is in the molasses layers. Make sense? This is a memory referencing bugs example. If you want to know what a memory bug looks like, you can take a look at it. I don't want to spend a lot of time looking at it now because we've got a whole section talking about it. And I think you guys have probably experienced plenty of memory bugs in life. But the answer is, like in most situations where you have these terrible errors, right, the actual output of this code will be different depending upon the environment. Will be depending upon exactly where it's executing. And that can make it hard to find a problem. Okay. Unlike Java, Python, most higher level languages, there's no intrinsic memory protection in C. It's possible that at one point in your C program, you overwrite a variable, and your program continues to execute. For milliseconds, seconds, minutes, hours, days, months, years, decades. You may wait around forever to find out that the answer to, to the question of life and everything is 43. For those who didn't get that, it's obviously 42. Okay? Why? Because you corrupted memory at one point in life and didn't go back to look at the memory you corrupted until later. That's a terrible error. Can you imagine trying to debug an error that happened 70 years ago? Right? In fact, when I'm programming, on the extremely rare, I mean, it happens like once every 30 years, in the extremely rare case that I make a mistake, and that mistake is a memory error, I thank God for seg faults. In fact, for anybody who doubts, I think seg faults are 100% positive proof, more so than gaps in the fossil record, that in fact, God does exist and loves you. Every time I get a seg fault, I say, thank God, God loves me. Why? Because when I get a seg fault, my program stops and says, you have a problem, and it's right here at this memory address.
What if you have a 6 degree antler?
Okay, that's great. That's a lot better than discovering that problem 70 years later and not knowing where it is when I get the wrong answer. Inexperienced programmers curse at seg faults. Experienced programmers know they got really lucky. And now they know where to start looking. And I don't care about your religion. You can believe that God loves you or not. It's fine. Okay. So C doesn't have the memory protections of these higher level languages. So we have to deal with that. We have to deal with the fact that we may get a seg fault, or even worse, we may not. And our programs may just keep running. Very painful. There's more to performance than asymptotic complexity. You remember in 122 and 210, in whatever sophomore level data structures course you happen to take, you were talking about algorithms analysis, and they said what we always do is this thing called big O. It's a type of asymptotic analysis. We look at what happens when the problems become really, really big, because who cares about dinky little small problems anyway? And we care about the shape of the curve, because eventually that becomes controlling. What is eventually? For some n greater than n naught. Great. Okay? Talk about the analysis some more, and they say we throw away the constant, because it doesn't control the shape of the curve. It may control its dilation, but it doesn't control the shape. Forget the constant. We care about the end behavior. Cool. But I'll tell you this much. As an end user, I care if something takes 1 second or 10,000 seconds. Right? Sometimes that constant actually matters. Why don't you use the Keston phone instead of the Samsung phone or the iPhone? Look, it has essentially the same feature set, but the Keston phone runs 10,000 times slower. That startup, instead of taking 1 second after you enter your password, it'll take 10,000 seconds. And when you tap an icon, instead of happening in a millisecond, it'll take a second. No one would use that phone. Right? Who would use that phone? No one. Right? In the real world, those constants matter. And in the real world, sometimes really small things make a difference. For reasons we'll talk about later in the semester, if you look at these loops and you see I and J and I, you'll find that the two loops, right, those nested loops are in different order there. One's Ji, one's Ij. I nested within J versus J nested within I. Okay? In this case, right, one version is 21 times slower, at least on the Pentium 4. Why? We'll talk about that when we get there, but it has to do with that memory hierarchy we talked about, and using things that are in the faster parts of it. Okay? Computers do more than execute programs. Well, one of the important things that we've got to think about, and it's ignored in many of the intro classes, right, is that you've got to feed the beast. If a computer is doing data processing, you have to get the data in. Right? This is true for traditional data processing. It's true for big data applications. It's true for network applications. Somehow, right, programs need to process inputs. It's only so much fun to compute the digits of pi. right? At a certain point, computers want to solve real-world problems with real-world data. So input is very important. Output is also really important. Sometimes you want the computer, the processor, to be able to control the machine, to do things. The output of a program, right, is actually changing something about the device. Making a phone ring, turning a light on, right? Sometimes it's sending the data somewhere else, to disk, to an SSD card, over a network to someone else, right? But unless we have inputs, we can't react to the real world. And unless we have outputs, we can't affect the real world. I/O is really important. The role within our curriculum. 513 is critically important for a huge number of classes. At the end of the day, any of the classes in CS or ECE that require building things in software require 213. It's really that simple. That's not all that there is to computer science. Okay? There's a lot of theory that doesn't require 213. That's not all there is to engineering. Okay? There are a lot of aspects of engineering that are very mathematical. Okay? Or don't build things in software or model them with software. All right? But for a huge number of courses, 213 is a prerequisite. And this is only a subset. This doesn't include things like the graphics classes and the animation classes, and. Okay? 213, when this course was first developed, was really revolutionary in computer science education. All the courses that tried to do the same thing, for year after year after year, for really decade after decade, were system-centric. Okay? They were classes about the machine for people that would build the machine. Right? 213 is different because it's a course about these systems for the people that program these systems. And that's a really different perspective. We're not writing the assembly, we're reading it. We're not building the memory controller, we're optimizing for it. Does that make sense? Okay. So we'll talk about hardware issues, computer architecture, operating systems, compilers, networking, and so on. I/O subsystems. But we're not going to look at them from the perspective of those.
Checking one of the terms you used.
No.
Okay.
Take notes. Dictionary will be available later.
Okay.
Or raise your hand. Which term?
Cache.
Cache.
I never heard it properly defined.
Okay. C-A-C-H-E as opposed to C-A-S-H. Cache. I mean, cache, like money, is good too. But cache in this case, the literal definition is something like a safe place to hide things. Like an arms cache. Like the military is going to store a cache of guns somewhere in case they need them later. Okay? But in the context of computer systems, it's a fast access layer that's smaller than a larger, slower access layer. So your browser is a cache of pages you recently looked at, so that you can go back and look at them more quickly. The memory hierarchy has a small amount of really, really fast memory, so that things that you use very frequently, you don't have to get out of slower memory. That answer your question? Excellent. Okay, so, there are a whole bunch of different types of systems, and we have courses in all these areas, right? We have a computer architecture course, an operating systems course, a compiler course, a networking course, an embedded systems course, right? We have courses in storage systems, and so on. Those are for the people building these things. This course covers a slice of all of that material for the people using them. Okay? The really serious programmers. Okay? Our goal is to bring out the hidden hacker in everyone. And we believe that there is a hacker in everyone. You and you and you and you and even you. Look excited about your inner hacker. We're going to find that hacker. And when we do, he's going to be excited. I'm promising. We need a front camera so we can zoom in on people. Everybody here but me is missing the excitement on his face. How about you turn around and show everyone your excitement? I don't want them to miss. See that? Give him a turn around for just a second. Okay, hold that pose while the camera zooms. You got him? Excellent. Okay. Power programmers manage the flow of data, right? You can't have processing any faster than you can feed the beast. You've got to manage concurrency. Concurrency is really, 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 really important. Right? It used to be the computer had the processor. Okay? Now, my cell phone has multiple cores. Right? Your desktop has multiple cores. Sometimes you take advantage of multiple cores just by multitasking. Having your instant messenger running on one, your operating system on another, your word processor on another, and your browser on another. That doesn't really take an application layer programmer. But sometimes you have something you want to accomplish, and you want to accomplish it quickly. So you want to take all of that processing power and use it to attack the same task, rather than dividing it up among tasks. And that gets tricky, right? The old saying about too many cooks in the kitchen. Right? If I have one cook in the kitchen with one sink and one oven, right? One countertop, it might take 10 minutes to do something. If I have two cooks in the kitchen, I can't accomplish the same thing twice in 20 minutes necessarily, right? If I want to bake a cake, and baking a cake takes 45 minutes. If I have one cook, it might, takes that 45 minutes, right? If I put another cook into the kitchen, I'm not going to end up with 2 cakes in 45 minutes. In fact, if they both put flour into the same bowl, I may end up with no cakes. Right? If one of them turns the oven on, right, 2 cakes may go in, and then the first one turns the oven off, the second cake never gets finished. There's a lot of opportunity for concurrency control problems. Right? Maybe there's only one mixer. And now either somebody needs to wait or there's going to be a fight. One baker will live. The other fought the good fight. Okay. The teaching staff. Perfect. Myself, Seth Goldstein, Franz Franchetti. So the 3 of us are the faculty. You care about us. I mean, we're there to help you. We also have like a dozen and a half TAs. I think we've hired a dozen so far. I think we let 150 people off the wait list yesterday. So I think we're hiring another 6, something like that. So I think technically speaking, there's 13 today, and will be 18 by the end of the week. The TAs are tremendous. Tremendous. You will love them because they'll hold all these office hours, and the TAs hold office hours like for several hours a day, 6 days a week. Faculty members, we have a few office hours, but the TAs have many, many more. Why? There are a lot more of them than there are us. They'll answer questions on your email, like we will too, right? But if you mail the staff list, all of the TAs get the email as well as all the faculty, right? So if there are 18 TAs and 3 of us, they're 6 times as likely to answer than we are, right? It's great. So we're part of it, but the TAs are another part of it. So 15.213 versus 18.213. 213, 18, 213 are basically only undergraduates. 513 are master's students. 213 gets live lectures and recitations. 513 basically is going to be delivered by video. The thought there is that master's students, having more experience, more time management, are able to watch the video on their own time and get the value out of it. Whereas experience has shown that undergraduates need a little more structure. We're going to style grade in 213, but not in 513. And the reason there is just that we think we need to provide that input to undergraduates who are earlier in their careers. But graduate students who either have programmed as undergraduates and gotten that feedback already, or programmed in industry, even if as engineers, just need that feedback a little less. Everything else is the same. The TAs are the same, the faculty are the same, the lecture materials content the same, the labs are the same, blah, 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 blah. Textbook, the revolutionary Bryant and O'Halloran book. Okay. I say revolutionary because it really was. It was the first book that took this programmer-centered view of systems for the sophomore level courses. Been adopted by all the top universities in the globe, basically. What's really cool about it is Randy actually is a faculty member here. He was our dean until July, and Dave O'Halloran's also a faculty member here. Now, let me suggest that you actually legitimately buy the book, as opposed to ripping a copy from, I don't know, one of those random sites. Why, you ask, did you legitimately buy the copy of the book instead of rip a PDF from somewhere? So here's what I'd like to ask you to do. Either buy a legitimate copy of the book, or go visit Dave in his office with your PDF copy. And say, hi, Dave, I have a question for you about 213. He'll go, oh, cool, because he loves 213. And then plop down your laptop with a textbook. He'll answer your question, but you'll see steam coming out of his ears. Because it takes a huge amount of effort, right, to prepare and publish the textbook. A huge amount. He's here, I have my office down the hall from him. He's here till like 2 or 3 in the morning, right? You know, like every couple of years for like 6 months revising it. And apparently when you publish a textbook, so I'm told, the textbook company keeps most of the money, and like the people who write it get like, you know, pennies on the, you know, like a couple dollars per book or something, right? But when you like rip the PDF copy, they get nothing. And so he actually is here, and I can attest to it, right? Till 2 or 3 in the morning, like for 6 months, every couple of years. It's this huge investment. And so it really is cheating him and Randy if you don't actually buy the book. The course components, they're the lectures. These are great. My favorite part. They're my favorite part. It's the only part they let me do anymore. They won't let me do the labs. I've already done the labs. The recitations are really good because they're problem sessions. Okay? I tend to talk about the things that are important. My job, right, I believe my job as somebody lecturing is to communicate to you what you need to learn, right, and why you need to learn it. And something about how to go about learning it. And if you leave the lecture knowing those 3 things, knowing what you need to learn, motivated to learn it, understanding why it's important and why you should learn it, and knowing how to go about learning it, I've been successful in lecture. I don't think you can absorb all of 15.2.13 in the, I don't know what it is, you know, we have 15 weeks, an hour and a half, we have in 3 hours a week, 45 hours of lecture. It's just not possible. Okay? What you can do is learn what you need to learn why it's important, and how to go about learning it. I think that's why lecture is important. And then you can go, right? And you can start reading your textbook. You can start doing your labs, doing the problems, and then you can actually learn. Okay? And so lectures are important because they help you understand what you need to learn, why you need to learn it, and how to go about learning it. Recitations are really important because it's an example, it's a great forum for seeing examples, okay, which are an important part of learning. The labs are critically important, and perhaps the most important part, because you can get your fingernails just dug in, right? That's where real learning happens, right? The rubber meets the road. You actually get your fingers in it and start to do things, okay? And studying for the exams, the midterm and final, is also a critical part of the course. Because in studying for those exams, they're problem-oriented exams. You'll get a lot of experience solving very interesting problems. And you're going to learn a lot. So I think it all works together. And now, right now, I'm going to give you, right, and our studio audience, and our distance audience, the secret to getting perfect scores on the exam. Okay? On the course website, we have published like every exam problem we gave from like 1999 through a couple of years ago. Okay? So here's what you should do. In the next couple of days, go and print every exam we gave in the last 5 years. Every midterm and every final. Print them out. And then take the last 2 or 3 semesters that we have and just sit them aside whole. Okay? The most recent 2 or 3 midterms, the most recent 2 or 3 finals that are up on the website. Take the rest and sort them by problem type. you'll see the problems tend to fall into a few different categories of problems. And just make a stack. Okay? Integer problems, floating point problems, simple assembly problems, struct problems, okay? Virtual memory problems, process control problems, concurrency control problems. Okay? Make several piles. And then when we come to lecture, we're going to tell you all about things, right? We'll have a lecture on integers, a couple of lectures on floating point numbers, blah, 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 blah. So here's what you do. After lecture, review your notes, read the associated part of your textbook, and then go straight for that pile of problems. And start doing them. Check your answers. The answers are there too. Do them until they're boring, not because you're tired, but because they're all easy. Get help if you need them. If there's some you can't get help, you can't figure out, talk to your friends. Friends are great. Okay? That doesn't work? Come to office hours. Mine are the TAs. Or Seth's or, whatever, right? Come to the faculty office hours. Come to the TA office hours. Email the course list. Right? Email is great. You'll get an answer if you say, hey, right, I'm having trouble with this. All right? Do that every class. Don't let yourself get more than a class behind ever. Okay? Try to do Tuesday night or Wednesday. Try to do Thursday night or Friday. If you fall behind, get caught up over the weekend or Monday. But don't go into Tuesday not being caught up. If you do that, you're basically guaranteed to get an A on the exam. Nothing here is so complicated that anybody who gets into Carnegie Mellon can't do. Okay? Nothing. Some people will find it easier than others. That's okay. It'll take some people, more or less time to learn than others. That's okay too. If you keep up as you go along, everyone here can get an A. It's really that simple. Okay, can you stop texting? Don't text. Put your phone away. Okay. So that's the secret. Then, about 2 weeks before the midterm, you remember I told you to set about 3 exams aside? Take one whole exam. From start to finish. Give yourself an hour and a half to 2 hours to do it. See how you do. If anything was uncomfortable to you, or if you missed anything, go back to your pile of exam problems and drive down again until you're comfortable. Then go back and take another exam. Repeat as necessary. You'll be getting hundreds on the exam, I think, before you get through 3 practice exams that way. If not, go to your pile of exams and make yourself a new exam. One problem one problem A, one problem B, one problem C, one problem D, one problem E. Staple. There you go. There's a new practice exam. Repeat until you got it. When it comes to the final, do the same thing. Okay? That's the secret. Somewhere in the syllabus, I think it still has the language that says to prepare for the exam, read the textbook 3 times. I mean, do that if you want. That was written by the person who wrote the textbook. But my feeling is, dive into the problems. Okay? Read the textbook as you go, right? Read the textbook if you're confused and miss a problem. It's a great resource. But when it comes to the 2 weeks before an exam, I wouldn't dive right back to the textbook. I would dive to your problems. Do them as you go. Review your notes. Read the section of the textbook. Do the problems until they're boring. Do that all semester. It'll probably take you 3 hours to do that, right, twice a week. Maybe 4. Probably 3. Okay? But then when you get to the midterm, you're ready. You'll take 2 midterms, 3 hours of work, and you're ready for the midterm exam. No stress. No fuss, no mess, full confidence. Does that make sense? Okay. Getting help. The course webpage has a bunch of resources, including the lectures, the exams, the assignments, and so on. We don't use Blackboard for the course, except for the fact that it's used to authenticate access to the videos. So if you were enrolled in 15.5.13, you have access to the videos. I do not believe at this point in time we're going to make them accessible to the 213 students. We're going to talk about that at the staff meeting we have on Thursday. Okay. We won't be using Piazza. I get asked a lot, why don't you use Piazza? Okay. The reason I don't use Piazza is I don't think it improves learning. Period. Okay. That is the singular reason I don't believe in using Piazza. And here's why. Okay. When you guys go to do labs, you're going to start writing the lab, you're going to run into some problem. You're going to try to push and push and push, and eventually you'll figure out what the problem is and try to solve it. Occasionally you'll get stuck and email the staff list, and we'll figure out where you are and give you some hints and help you get unstuck. So you as students are going to have to learn to find the problem, to solve the bigger problem, to find the small stumbling blocks, and to push at them, and to ask questions about it. What happens with Piazza, as nearly as I can tell, is the first cohort of students to start and move the fastest run into all the interesting cases. They ask about them on the bulletin boards, they get answers. And then what happens is everybody following behind them doesn't have the opportunity to think about it. They've already been predisposed to know where the problems are and predisposed to know about the solutions. And now they're not learning the problem solving. They're not learning the issue spotting. They're not learning to think about, I have a problem and I have tools, which tool is the right one to use for the problem. They're told, when you get here, use this tool. When you get here, use this tool. They're getting a much cheaper experience. And so, yes, it does dramatically decrease the number of questions that are asked on the staff list if you have Piazza. It does decrease the number of times you have to answer the same question. We'll answer the same question sometimes 80 times on the staff list. It's unusual for it to be that many, but it could happen. Occasionally does. More often than not, we'll answer the same question in a class this size 5 to a dozen times. And you know what? That's okay. I am happy to answer your question when you ask it, and give you the answer that's right for you, and answer your question when you ask it, and give you the answer that's right for you. And to give everybody the right answer to the right question, most importantly at the right time. So my goal in avoiding Piazza is to ensure that students learn as much as possible, period. Right? Even if that means that we answer more questions on the mailing list. Even if that means we answer questions repetitively on the mailing list. When we see that we're getting asked questions repetitively on the mailing list, we have a choice, right? We can say, this is great. These people are running into this interesting problem. We want them to. Some of them we encourage, some of them we help, whatever. Or we can say, you know what? We should have really explained that better. We now know that 80 people are confused about it. And now we can improve the course. As opposed to on Piazza, where the first person runs into it, we answer it, everybody else sees it, and we have no idea how common that is. So that's my story on Piazza. I'm sticking to it. Getting help. The fastest thing to do for help is send an email to the staff list. Why? Somewhere between 13 and 18 people, plus 3 faculty, so 16 to 21 people are going to be monitoring that list. It's much better than mailing just me, because when I'm in here teaching this class right now, or my other class at 1:30, or in staff meetings at 4:30, right, some TA is answering questions on that list. Right? When I'm up until 3 a.m., I'm answering questions to that list. One of the early risers on staff probably starts answering questions at 7:30 in the morning. Right? It's just a whole bunch more opportunity. Office hours will be starting on this Sunday. They're going to run Sunday, Monday, Tuesday, Wednesday, and Thursday, not on Friday or Saturday because no one comes. We're going to go from 6:30 to 8 p.m. We're still talking about what room it's going to be held in, so give us a couple more days on that. We'll know that on Thursday afternoon. We're going to talk about it during our staff meeting. If you really need a one-on-one appointment, then feel free to request one. In general, it's best just to show up at office hours. because, A, you'll get your question answered. B, you can sort of be part of a discussion that may involve others, and some of their questions may be interesting to you too. You're also likely to find office hours, from 6 to 8 p.m., which is really easy to get there, and one-on-one appointments may take a day or two to schedule. Work groups. So you must work alone on assignments. Your assignments are to be done individually. Okay? Don't work on teams, blah, 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 blah. But study groups are great for doing the practice problems. They are fantastic. Right? Order some pizza, get together with 3 or 4 friends, do 5 or 6 problems. You'll have a good time. You'll have more fun than doing it by yourself. When somebody has a different approach to a problem than you do, you'll get to see that too. If you get stuck on a problem, somebody else will be able to explain it to you, and vice versa. It'll be great. Hand-ins are generally due at midnight, 11:59 p.m. So if we say it's due Tuesday, it's due before Wednesday, right? 11:59 p.m. on Tuesday. If there's some irreducible conflict, let us know. There's not going to be, because we're going to do electronic exams this semester, and so you'll be able to schedule a time slot of your own choosing. So there shouldn't be any of those conflicts. If there's a problem with grading, please let us know within a week. Do it in writing. That way we don't lose track about it, and we can talk about it at the staff meeting. If you ask one of us in the hallway, we don't have the opportunity to chat about it at the staff meeting, right? Because, we're never going to remember. The syllabus has a detailed procedure. Basically it says, tell us what the problem is, slide it under one of the faculty members' doors. In terms of computing resources, we can use the machines donated by Intel, shark.ics.cs.cmu.edu, or unix.andrew. Either work. You get 5 grace days this semester. The last assignment is due, and the last assignment is due. You can't use any grace days there. The reason for that is we want to make sure that people don't push that assignment late and then get stressed out for finals. At a certain point, it's better just to draw the line, turn it in, sync point, right? Lateness penalty after you use your grace days, or the limit of 2 grace days per lab, there's a 15% penalty per day. No hand-ins after 3 days. So the most late you can be on an assignment is 3 days late. The reason for that is to make sure that you have enough time to do the next assignment. Right? Comes to that sync point thing. In the event something really bad happens, a major illness, death in family, blah, 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 blah. This lateness penalty stuff is obviously not the right answer for that. Right? That's stuff that affects you across all of your courses. Go talk to your academic advisor. Explain to your academic advisor what's happened, where you sit in your classes, and put together a plan to get caught up. And then your academic advisor will email us and say, hey, this person needs you to do this for them. Okay? And then we will. If your academic advisor says give you, 10 extra days, that's fine. Your academic advisor says they get caught up over spring break, that's fine. Whatever it is, we don't care. Right? As long as we know you've chatted with your academic advisor and it's going to be part of a good solution for you, we're okay with it. Big advice we have is once you start getting behind, it's really hard to get caught up, right? Because to get caught up, you need to be able to maintain the normal course pace plus the catch-up stuff, right? That's much harder than just keeping pace. So start early is our general advice. Work hard, finish early, all that good stuff. Okay, look. Don't cheat. Here's what we know, okay? We know that this is perhaps the best-selling textbook for this course anywhere in the world. We know this set of labs that come with the textbook, right, is perhaps the most popular set of labs for this course anywhere in the world. We know that students all over the world have posted answers to these labs in any number of forums. Okay? Dave O'Halloran has made it his life's mission to find every one of these and add them to our database of solutions that we use when we run MOS. Okay, it's run automatically by AutoLab. Every time you turn in a solution, okay, AutoLab has it. And then at the end of the lab, Moss is run and gives the report of what solutions match each other and what solutions match the ones Dave has put in there. Okay? Now, I'm the one who follows up on those. I can assure you I follow up on every one of those. But those of you who know me know there's an expression on campus. It's called Kesden time. 5 minutes late-ish. Okay? I don't necessarily follow up on those immediately. So if you turn in a solution to a lab and it's copied, it's not like red lights are going to flash and bells are going to ring all at once. If you do that for 3 labs in a row, I may not notice until I get around to looking at the Moss results the last couple of weeks of the semester. But I do. We prosecuted 20 some odd cases of cheating last semester. 2 students were thrown out of the university. 1 more is a hearing coming up to discuss the same. Don't cheat. It's really serious. Okay? I mean, in one case, I submitted a report that, within days of another instructor submitting a report. That student got thrown out. In 2 other cases, it was a second offense that, in another case, we don't know the outcome of this one, I don't think yet, it was somebody who cheated twice in 213, a year apart. Just don't. We can Google too. Okay, my personal favorite case, I have several personal favorite cases. One of my personal favorite cases is somebody was at a Google dinner, a Google intern dinner, okay, bragging about how she did all of the labs for her boyfriend who was a Stanford student. Great. Well, who else is sitting around the table at a Google intern dinner, do you think? Right? A bunch of 213 TAs who happen to be Google interns, or at least were at some point in their career. Okay, so I don't remember whether it was actually a Google intern or one of the Google mentors. But it took like 6 seconds from the dinner table, right, for somebody to text both me and the instructor at Stanford. That person got busted. Both of them got busted. Right? Don't. I don't know how it is that we managed to bust anybody during the semester, because you know what we do. We have all of your solutions in Autolab. We run Moss against them. And if you think that Stanford and CMU and Berkeley and MIT, and Cornell and so on are very far apart, take a look at our faculties and realize that we're all alums from other places. Right? Our students mix. Right? It's just not going to work for you. My other personal favorite was a case where a student cheated. The code exactly matched something from GitHub that Dave O'Halloran found and put in the database. Thanks, Dave. I call the student to my office. The student immediately starts confessing, which is good. I mean, that's actually the right way for this to happen, right? But the problem is the student's confession didn't match what I was looking at. I was looking at the student's code and GitHub code, and they were exactly the same. And the student was confessing to getting too much help. The student said, "I am so sorry, I know I shouldn't have done it. I was having a whole bunch of trouble with the course, and I was really struggling, and my father decided that he needed to hire me a teacher to help me. And so he got me this teacher, and I got too much help from this teacher, and I know it. I know I shouldn't have gotten that much help." And I said, "Well, that's really interesting." And he said, no, I'm so sorry. The guy's practically in tears confessing to getting too much help from this teacher. I said, but the problem here is that your lab matches GitHub. I know nothing about this teacher. And he says, no, it can't. Yes, it does. Here. And so apparently his father hired him, this faculty member at the University of Outer Mongolia. I'm not making that up. Some teacher Peng. And there's some Chinese equivalent of Skype, and so he Skyped with this person in China. who helped him with his lab. And apparently the way this guy helped him was by feeding him lines 3 lines at a time from GitHub. So as nearly as I can tell, neither the student nor teacher Peng could do the lab. So this poor person's father paid this teacher in China to rip code from GitHub and feed it to him over some Chinese Skype-like service. Don't cheat. We will catch you. We will. Really, honestly, truly. It's not that it's our life work, it's just it's not hard. We have a database of solutions and a tool that compares them. There's a button on the lab panel that says, find cheaters, run MOS. Don't cheat. Laptops are permitted in course for looking at slides you previously downloaded or taking notes, but not for electronically mediated communication. Presence in lectures is voluntary. Take no recordings of any kind. We'll provide the videos for the 513 crowd. Exams, 20% for the midterm, 30% for the final. Labs count half. Their weight varies. The simpler, shorter labs count less than the longer, more involved labs. Topics, integers, floating point arithmetic, assembly language programs, how C is represented in assembly, data structures are represented in assembly, certain aspects of architecture and compilers. The first 3 labs play with those topics. Next set of topics we cover, the memory hierarchy, caches, disks, spatial and temporal locality, and certain other aspects of how the operating systems manage these. The cache lab, lab 4, covers these. Hardware exceptions, processes, process control, Unix signals, non-local jumps. This is covered by lab 5, the Tish lab, where you write a shell. Virtual memory, address translation, dynamic storage allocation, caching involved in there like the TLB. This is tested in the Malloc lab. Networking and concurrency control. This is tested in Proxy lab. Okay? The idea behind all these labs is the same. Give you a well-defined goal, some problem to solve, and let you loose to actually build the solution. You'll pick a handle, a name that's not yours, nor the name of any faculty member or TA. Okay? Some alias, and it'll rank your solution on the scoreboard. Okay? And so at a certain point you get full credit, and everything after that is for bragging rights. Okay? That way you know that you can stop at a certain point, but if you really want to keep driving forward and somebody has a faster malloc than you, well, you know it's possible you can drive forward and try to leapfrog them, if you want. Labs are submitted via the AutoLab system. Basically, point at it and go. As of today, if you're enrolled, you have an AutoLab account. If you don't, if you just enrolled more recently than we added them at 10 a.m., we'll get you your account tomorrow. Waitlists, if you're trying to get into the 15 section, talk to Catherine Fichtner. If you're trying to get into the 18 section, talk to Zara Collier. If you're trying to get into 15.513, you should already be in. If not, you're not seeing this video, because the video is behind Blackboard, which is registration controlled by the list of people who's in. Don't contact me or the other instructors. We have no control over the waitlists. Guys excited? Yeah. Yeah, I'm excited. Have a great day, everybody.